Hello there, it's your friendly heavy physics teacher again. This time with a lesson for my Regents Physics class. This is covering Unit 10, Lesson 6, our lesson on transformers. Now we're talking about the electrical kind of transformers, not robots in disguise, unfortunately. As big a fan as I am of Optimus Prime and Ironhide and, those guys. Nope, we're not going to be talking about anthropomorphic robots that can change into vehicles. Okay, we're talking about electrical devices that transform the voltage across them, changing it from one amount to a different amount without changing the energy. There's a key. We get no change in energy. Okay, give me a moment. Okay, now we cannot talk about transformers and leave out one of the most momentous fights of the modern industrial age that occurred around this whole principle. Okay? So, some historical background. 1820, Hans Christian Ørsted discovers electromagnetism, publishes it, and it gets out to the world. During the 1820s, Humphrey Davies and Michael Faraday begin work on it. Michael Faraday pursues it. It becomes a passion with him. And in 1831, he publishes his definitive experiment that shows what an electromagnetic induction is. And I'll get to that in a little bit. So in 1831, he publishes that principle. And then by the 1840s, he's really established a whole bunch of a set of empirical observations, meaning he's done experiments, he's used physical things to show how you can use this interconnection of magnetism and electricity. He lays the principles for electric motors that we use. He lays the principles for creating galvanometers, which were the electromagnetic devices that you could use to measure electricity. A galvanometer, with only a few changes to it, becomes an ammeter or a voltmeter, depending on how you wire it. And so he lays the foundation by the mid 1840s, along with James Clerk Maxwell's publication of the math that explains electromagnetism in the 1850s. We get you know, an amazing advancement in science, the science of electromagnetism. Well, here in America, a very famous experimentalist takes it up and decides, how can I make money on this? He invents the stock ticker thingamajigger. Basically, it's a form of Morse code device, okay, that is specifically for transmitting stock prices. And it creates the ticker tape. And that is how the stock market, he makes his money initially having patented that machine. Okay. And he then goes on to invent the phonograph. And he invents a whole bunch of other electrical devices that are using the principles of electromagnetism. And he creates a company, and he calls it General Electric because it's dealing with everything electric and how we can use electricity to modernize our lifestyle. If you haven't figured it out yet, it's Thomas Edison. Okay. And one of the big things that he's promoting with General Electric is building bigger and bigger and bigger electrical machines. Okay. And it becomes evident very early on to not only just Edison, but also in Germany, a gentleman by the name of Siemens, who you will recognize. Siemens is to Europe what General Electric is to America. Okay. The Philips company in the Netherlands, all of these industrialists, all of these electrical industrialists come to the fore in the 1860s, 1870s, 1880s. Okay. By 1882, Edison has been commissioned to um, develop the first commercial power generation system. It goes online in London, and then another one goes online the next year, I believe, 1883, or it might be 1881 and 1882. Here in New York City, he brings the first industrial commercial power system online for generating electricity and supplying it to consumers. Okay, he's using direct current devices. And the problem with that is that if you're going to produce, let's say, 100,000 watts of power, and the voltage you need to produce it at is the voltage it's going to be used at, say, 220 volts, that's what Edison actually proposed to be the voltage that would universally be used, 220 volts. You would need, if you're going to produce, let's say it's 200 volts, if you're going to produce 100,000 watts of power, that means you need, see, 200 volts times 500. There you've got your 100,000. 500 amps. Driving 500 amps through a wire creates a lot of heating in that wire, even if it's 1 ohm of resistance. That is a lot of heating in that wire. Okay, 500 amps squared times 1 is the power loss. So 500 squared would be 25, 250,000? Yeah, so you're using up all your energy just pushing it through the wire. So the wire has to have as low resistance as possible, and the distance of transmission needs to be as short as possible. So Edison was proposing that we build power plants every few blocks in the city, and that would supply the energy either for the industrial complex or for the community surrounding it, so that transmission would be relatively easy to do, and you wouldn't get a lot of electrical losses through the power lines. Because the longer the power line is, if you recall from resistivity, the longer the power line is, the more resistance that wire has. Okay? Well, there was a Polish immigrant to America who was enamored of electromagnetism, was enamored of electromagnetic waves, had practically put Maxwell's equations to memory, and he was inventing all these ways of trying to get electricity transmitted for free. He didn't like the idea that it would be limited to only those who could get connected to it. And he tried out all of these different electromagnetic systems, which work, interestingly enough. Look up Nikolai Tesla's work. Some of it looks really scary, but it's actually pretty safe. And it would broadcast electrical energy to anything that could receive it. Now, he also liked to vacation up to Niagara Falls, and he would look at the majesty of the falls. And I've been there, and it is indeed an incredible, incredible natural phenomenon. Okay, but of course, being the engineer that he was looking at that and going, that's an awful lot of energy. Wouldn't it be great to harness some of that energy? He happened to be friends with an industrialist by the name of George Westinghouse, who was a competitor to Mr. Edison. Now, what Mr. Westinghouse was doing was simply inventing different kinds of electrical machines from what Edison was inventing. And he'd redevelop them, he'd change them, he'd make different efficiencies, he'd make different applications. And so the Westinghouse Corporation was in direct competition with General Electric. And Westinghouse and Tesla had a meeting. Whether it was a social gathering or not, they met in some fashion at Niagara Falls. Both of them enamored of the power of the falls. And it was Tesla that suggested to Westinghouse, I'm pretty sure I can figure out a way that if we can generate electricity here, we can get it to New York City. We can get it to Buffalo. We can get it to Cleveland. Okay, we can get it to Toronto. All right. All of those cities are not next to Niagara Falls. Buffalo is a good 25, 30 miles away. All right. New York City, of course, is 350 miles away. All right. If we're going to talk miles. All right. Buffalo's 50 to 60 kilometers away. New York City is approximately, 500-ish kilometers away. So how do they get that energy across New York State, across the frontier of Canada, across the Ohio coastline of Lake Erie without huge attenuation losses from the high currents that you would need normally to transmit through those lines? Well, Tesla was thinking, if we can boost the voltage, the current's going to decrease. If the current is low, we can transmit very high voltages across transmission lines with low current and then step it back down for use by the consumer wherever it needs to be used. Okay? This created an opportunity for Westinghouse. And he lighted the World's Fair in Chicago. I believe it was the 1903 World's Fair, using his system of alternating current. He and Edison then had it out publicly, very publicly. And Edison was warning about all the dangers of alternating current and proceeded to show some, electrocutions of things that are actually quite disturbing. Westinghouse turned around and talked about all the dangers of direct current. And they called each other names in the press. Oh my goodness, it was incredible. And eventually, Westinghouse, by lighting the World's Fair, safely lighting the World's Fair in or the early 1900s, convinced the political establishment that we would use AC rather than DC. And that's why we have the power transmission grid that we do today that uses primarily AC to get energy from place to place in our country. So, how does that work using the principle of electromagnetic induction? Okay, this was Faraday's setup for his original proof of concept of electromagnetic induction. And what he did was he had this iron ring that on one side of it he wrapped around a coil of wire, and he had that connected to a DC electrical source because that's all he had at the time. And it had a switch on it. Okay, and then he had the ring, and on the other side of the ring he wrapped more wire, and he wrapped the same amount because he figured that I needed the same effect on each side. Okay, and then he had that, and he wrapped it around a compass, and he told everybody, notice the way the compass is pointing. All right, now if I close the switch, that's going to cause a current to flow in this coil over here. That current flowing as it goes from 0 to some number, whatever the current is for the wire, all right, that's going to create a magnetic field, a change in magnetic field that's going to happen in the iron core. The iron core is going to essentially transmit that change through it through its domains. Okay? And so that change in magnetic field then affects this coil of wire over there. Aha! There's the concept of the change in flux. Okay? So this quick change in current over here causes a change in the magnetic field in the ring. That changing magnetic field affects the coil of wire over here, and you get a momentary deflection of the needle as the electromagnetic coil over here affects it. Once the current on this side over here becomes steady, there's no changing magnetic field anymore in the iron core, and so there's no changing magnetic field across this coil. And so that means that even though there's electromagnetism over here, this side won't have a current flow. There's no change in the magnetic field across this coil, so there's no EMF induced over here. So this goes back to pointing the way it did. Turn the switch off. That means the current stops in this coil. That means that the magnetic field here collapses. That creates a change in the magnetic field on this side of it too, the same collapse. And as that collapse happened, that changing magnetic field creates a change in flux. And for that period of time, that instant in time that it happens, changes, it induces magnetism over here. And so what you could do is you could push the switch on, turn the switch off, push the switch on, turn the switch off, push the switch on, turn the switch off. And you'd notice that the compass needle over here would do this every time you created that change. It would go from pointing the way it normally would to pointing with the field to that, so on and so forth. Okay? And so this was his proof that if you create a changing magnetic field, then that changing magnetic field is going to induce the EMF that can create a change over here that we can witness. Nikola Tesla said, what if we change the number of wraps of wire here? Because we know that if I take a coil with more coils of wire and I put the same amount of current through it, I'm going to get more magnetism because of that. Okay? Let's do it the other way. What if I take more coils of wire and have the same magnetic field affected? Do I get more electricity? We showed that I showed that using my coil system in the last video. When I increased the number of coils, I increased the amount of electricity that was being generated by the same number of magnets. Okay? And so that's the principle that Tesla says, all right, let's make a change to this. So here we go. This is Tesla's variation on his setup, on Faraday's setup. He says, okay, instead of a DC power source, we're going to use an AC power source. Okay? And it's going to create a varying voltage, which in this coil is going to induce a varying magnetic field in this iron ring. That varying magnetic field in this iron ring then is going to induce an EMF in the wire, and that wire then can be used to transmit to something that we can use it. It's going to be continuously changing, so that means we're going to get a continuous change over here. We get a continuous flow of electricity. We get a continuous flow of electricity. 2, we've got a certain number of coils of wire here. I have a larger number of coils of wire over here. So that is going to induce a larger EMF on this side. I get more voltage. The price I pay is that the current over here will be low. Think about this. Can the energy supplied by this get increased across this iron ring to this side going out? Can the energy from this generator get increased simply by moving across the iron ring? If I push on one side of a lever, does the energy going through the lever get increased by the lever to move the object on the other side of the lever? Does the energy from a battery get increased by going through the wires to the light bulb it's going to use? No. Conservation of energy means that the maximum I'm going to get, the energy out here, is going to be the energy that goes to the far side over here. Voltage and current will change, but the energy across the transformer will not. So what's creating the change? It is this difference in the number of wires. And it's that simple, believe it or not. Okay? The ratio of turns of wire in the transformer from the primary side is the input side, to the secondary side, the output side. Okay? So if the ratio of the turns of wire from the primary to the secondary create that change in EMF across the transformer. And so we can show that relationship. Number of turns in the primary divided by the number of turns in the secondary, the ratio, is equal to the number of the voltage of the primary compared to the voltage of the secondary. Okay? All right, I'm returning back to this diagram. This right here would be my primary coil. This right here would be my secondary coil in this example. This would be the input side. This is my output side. Primary, secondary. Okay? There are situations where we do it the other way. The primary side is going to have more coils in it. The secondary side is going to have less coils in it. Okay? And so depending on whether you want to boost the voltage up or boost the voltage down, turn the voltage down, depends on whether your primary is going to have more or less coils than your secondary. Okay, for an ideal transformer, and we're going to just deal with ideal transformers. Interestingly enough, for real transformers, the transformers that are out on your power pole, the transformers that are out at power plants that are being used today, they have like a 98% energy transfer efficiency. So they're really close to being ideal, okay? But we're going to talk about purely ideal, all right? Which means the power in equals the power out, or we can say the power in the primary coil has to be the power of the secondary coil. So, since electrically power equals voltage times current, so our primary relationship is here, secondary relationship is here, and because a transformer is transforming the voltage, that means that since the primary power must equal the secondary power for conservation of energy, then if my voltage increases across the transformer, it must decrease the current. It must decrease the current. And there is Nikola Tesla's leap of understanding that if I'm going to boost my voltage, I can transmit a high voltage across long distances because I'm going to have a low current comparatively. Now, you remember back at the beginning when I described the situation, let's say that they needed 100,000 watts of power to do a particular thing in an area. Okay? And if they're going to generate it at 200 volts, so my numbers are nice, then they would need 500 volt or 500 amps. They would have to produce it at 500 amps in order to get that 100,000 out. Okay? Tesla says take that 200 volts, boost it 1,000 times. 200 volts now goes to 200,000 volts. That means only half an amp has to flow through the lines in order to get that 100,000 watts of power from the power generator down to where it's going to be used. That's the beauty of the AC transformer system for transmitting electricity. I'm not changing the energy, but by increasing the voltage, we decrease the amount of current that needs to flow through the wires, and therefore we decrease the amount of energy loss that's happening in those wires because of the resistance of those wires. Okay? That's why we use AC. But as you know, that's not an AC system. This right here uses DC because it uses batteries. And so when we plug in to recharge it, or your phone to plug in to recharge it, we're not actually sending AC into it. Nor are we sending the voltage in that's coming out of our outlet. Our outlets are 120 volts. So now we've got a system that not only needs to transform the voltage down, but we also need to transform it from one form of current to another. Let me get to that in just a moment. Okay, now here's where we have the application of the transformers. A step-up transformer is one where the voltage in the primary is less than the voltage in the secondary. You are creating a boost in the voltage. These are used at power plants, okay? Generally, a power plant will tend to generate electricity at about 2 to 5,000 volts, all right? Simply because that's the scale that they can build their generators on. You know, the EMF, they put a huge number of turns of wire and they create an EMF that's, say, 2,000 volts, okay? And so now they're producing current, say 1,000 volts of current, so 2,000 volts, or 2,000 amps of current. So there you have 1 million watts being produced by that generator, a megawatt, all right? Now, that gets bumped up from 2,000 to 2 million volts. Well, that means that the current gets bumped down from 1,000 amps to 1 amp. Okay? That gets transmitted out to where it's going to be used. We don't use 2 million volts at our homes. Okay? They will step that 2 million volts back down to about 17,000 volts, about 15,000 volts, depending on where they are, depending on what the transmission lines will call for. Okay? And that means that there's going to be an increase in the current in that location. But at that point, the distribution is going to happen over shorter areas. So the losses are going to be relatively low still. Now, that 17,000 volts is what's coming to the power lines outside your home. It's one of the reasons why you don't fly a kite. Don't fly a kite near those power lines. 17,000 freaking volts in the power lines on top of those telephone poles. That's bad news, folks. 17,000 volts. That's gross. All right? That gets stepped down again. All right? The gray kind of cylindrical devices that are on the power poles that you then see the wires that get run from them to your home, they're stepping that 17,000 volts down to the 220, 120 that's going into your home. Okay? So we have basically a one-stage step up at the power line or a power station, and then a two-stage step down from the transmission from the power station to the local distribution into the wider network, and then once again a step down at your home. But that's still all AC. In the charger that you probably have your phone connected to, in the charger that is attached to this laptop that I'm recording this on, there is a device known as a rectifier. And a rectifier changes AC into DC. So your phone charger is actually two devices. It is a transformer transforming the 120 volts that's coming out of the wall down to either 12 volts or 9 volts, depending on how your phone charges, what your phone uses, okay? And also rectifies the AC into DC so that the battery storage system in your phone can then be recharged using the DC, okay? So there you have it, Transformers, mixing a little bit of industrial history with our knowledge of science, okay? Electrical transformers not only transform electricity, but they have transformed our modern style of life from what it was prior to the 1800s, prior to the 1880s, to today, being able to continue your education even though you don't happen to be in a formal classroom. This is your friendly heavy physics teacher signing off one more time. I don't know when I'll see you in the classroom, but I'll see you the next time we have an online session. Thanks to Transformers. Ta-da-ta-da. Have a good one, folks. Bye-bye now.